Thank you. Okay, yes, I was already introduced. So my name is Stefanie Appelgrün, and I was involved in this project as a student researcher at the Digital Design Unit, together with my professor Oliver Tessmann and also Max Eschenbach in my team. Yeah, so starting with the problem statement, we all know that that noise pollution is a problem and it's also continuously increasing, and this makes us sick, and so we have to find solutions also in architecture and also to find responses to make this more sustainable. And yeah, although there's already a wide range of sound absorbing solutions and materials, many of them are often very material intensive, also fossil based, and in general far from sustainable. But at the same time, we also see there's an increasing trend, or the number of 3D printing pillar projects in the built environment. But the acoustic properties of these buildings or building techniques remain largely unexplored, and no one cares about how they sound. So we don't really know what these buildings or rooms sound like. And yeah. If we look at the material, clay is of course not a conventional or classical sound-absorbing material, like the Symposium project we saw in this morning from Philipp Eversmann. Clay is due to its high density, its sound absorption is quite low in general, as shown in this graph. And it performs only slightly better than concrete, but still shows very low sound absorption, especially in the range about 500 Hertz, which is the most relevant for the room acoustics in architecture. So our goal was therefore to 3D print clay as a sound-absorbing geometry, while also taking into account environmental aspects and to think also in monomaterial systems. Okay, so with clay, we had a very sustainable material, everything was good, but it's also available in a lot of parts on our planet, but it doesn't really perform as a sound absorption material, as already mentioned. And to overcome this limitation, our idea was to recreate porosity and use additive manufacturing for this, which enables us the creation of very complex geometries that are impossible to achieve with conventional methods. And one really important, or the most important key parameter to improve this for getting a high sound absorption degree through generating porosity is tortuosity. Tortuosity is a value that describes the curvature of a geometry or the complexity of a pathway. So in other words, it means how much longer, how winding is a path or the sound wave compared to a straight line. So our goal was to create something that is complex, and yeah. So yeah, to achieve this, we used a special growth algorithm to translate the tortuosity into the print path or the print pattern. And for this, we used the differential growth algorithm. It all starts with an input curve, which is divided into a multiple series of seed points, and it can be connected to form curves or polylines with a complex system of branching and continuous channels in 2D. And we also can play with the parameters. For example, we can, the collision distance of the seed points can be defined to get different levels of porosity. And due to this growing mechanism, the geometry stays continuous, and this is very important for sound absorption. Yeah, so now we need to go from 2D to 3D, and to generate a three-dimensional space or three-dimensional pore space, we stacked our 2D layers on each other. And to avoid weak points, we also defined a syntax that plays between different input curves. And to achieve this, we alternated between biomorph and symmetrical curve inputs, what we call the syntax of the system. And we also defined different origins from where the pattern can grow from. And this is also leading to an increased tortuosity, which is, as mentioned earlier, really important for sound absorption. Yeah, so this is our first part of our absorption principle, but we also added a main structure to make the system more self-standing and also to make it more material efficient. And our wall system consists of alternating convex and concave curves, creating these pocket-like structure. So the sound waves can enter the small hole, and they will be reflected in this area multiple times. So they will lose its sound energy and will be absorbed in the end. And at those parts where there's no opening in the hole, we applied our growth pattern. So yeah, we developed these two principles of sound absorption. And how can we print it? We used in our university a 4100 WASP 3D printer, as shown in this graph. But it was only available for horizontal printing, and the nozzle could therefore only be standing in a vertical position, which was challenging because we had a very curved structure. And yeah, so with our printer, it wasn't available, or it wasn't possible to print the main structure and the growth pattern all in one. So therefore, we had to print them separately from each other. And yeah, so we had to print it both in a horizontal layer to rotate the growth pattern afterwards. And yeah, after a 7 days drying period, the printed parts were assembled by using slip joining. Slip is a mixture of clay and water, so we have like a slurry, which acts like a natural glue that also maintains the monomaterial structure, so you don't need to introduce any foreign materials or additives. Yeah, and finally, this is our prototype, which can be also visited in our exhibition. Yeah, so we had a very complex process with the assembly, but in future applications, we could also think of a robotic fabrication where the main structure and the growth pattern is printed all in one. So we could imagine there's two sequences. In the first sequence, there's a bigger robot with a bigger nozzle of 10 millimeters, let's say, and the main structure is printed by this robot, and this is followed by a second sequence where you have a small robot with a smaller nozzle that applies growth pattern on this. And for architectural use cases, the object is regarded as self-standing interior element that can be, or that separate room parts from each other. And what we also see here is the silhouette, which is silent in two ways. We have the pocket-based main structure and also the surface with its growth patterns. And we also wanted to quantify, of course, the acoustic performance and the sound absorption level, especially the level of sound absorption. So we also made some measurements in the impedance tube, and for this we prepared some different cylindric samples. So yeah, we started to print these small-scale samples in different sizes and collision distances to see if we can improve the geometry and also to find out the best combination of collision distance and size. Yeah, and we also got really nice results, and the highest sound absorption was around 86% at a frequency of 1600 Hertz. It was measured for, as we can see here, in a 10 millimeters sample, printed with a 2 millimeter nozzle and a collision distance of 6 millimeters. And on average, the fired samples outperformed the unfired ones, which also confirms that geometry can significantly enhance sound absorption through its geometry, even with acoustically rigid or raw clay. Yes, that's it. And I also would like to give special thanks to our partners from the Institute of SRM, System Reliability, Adaptronics and Machine Acoustics, also at Technical University of Darmstadt. Thanks for Dr. Robert Feldmann and Ali Muhavet. Yeah, thank you.
The floor is open for questions, and we have a first one.
Hello, thank you for your presentation, very interesting. I have just some curiosity related to, like, did you run ulterior tests, like in a reverberation chamber, to compare the sound absorption, like at the component level, like in a real space, for example, and also maybe compared to something else you could find in as an architectural product? Because what I see is that you're increasing the surface roughness, and I'm curious about this.
Yes, of course, and thank you for your question. Of course, we also measured it in a reverberation room, also at this Institute of SRM at Technical University of Darmstadt, and we also got the same results, about 70 or 80%. Yeah.
Okay, thank you.
Do we have more questions?
Thank you. Really nice work. Can you explain better how do you expand from the initial algorithm growing mesh for the larger scale? It was not really clear.
Sorry, again, I didn't.
You start with algorithm on the natural growth of the shape, and how do we expand this for the larger objects? The pattern.
Yes, yes. So you mean the robotic fabrication to
No,
scale it up, or?
The design. The algorithm design that you use for the growing pattern.
Yeah.
How do you expand for bigger surfaces?
Yes, maybe we could also think about this. Yeah.
Okay. No, just I didn't understand. So you're doing some samples, correct?
Yeah.
Some analysis. But how do you grow it for the overall? You have a specific syntaxes like that you defined. And how do you apply it for the final ones?
Yeah, yeah.
Just increase the size to scale it?
Yes, yes, I played with the size, yeah.
Okay.
Yeah.
More questions? There's one more. Last question.
Thanks for the presentation. You mentioned at the beginning that the absorption band was about 500 hertz, and at the end you showed the measurements where you have the 86% absorption at 2000 hertz. So how does this sort of come together?
Yes, the 86% was the highest value we got in general, but in the mid-frequency range, about 500 hertz, we also got values about 70%. So it's higher. It's significantly higher than with raw clay.
Do I need to come back with the mic?
Well, yes, I was hoping you were explaining because you have wavelengths, right? Sorry. Yeah, so I was hoping that you were referring to the wavelength, because if you scale your model, your physical model, you also need to scale the wavelength of your.
Yes, that's right.
So that was actually, so the 2000 hertz would correspond to the 500 hertz in your large specimen. If you, okay.
Okay, thank you very much.